All right. So integration by parts. Often abbreviated, it's just IBP. So what I would say about integration by parts is typically we only use integration by parts when we see what we call a mixture of things. So I haven't really talked about this terminology yet, but I'll say it right now. So we typically use this on a quote mixture integrals after we've tried U sub. So when I say a mixture, here's what I mean. A mixture of usually two, could be more, two or more types of functions. The types being logarithmic, algebraic, inverse trig. Oops, I wrote this in the wrong order. That's fine. Trig and exponential. So logarithmic is self-explanatory. Algebraic, when I say algebraic, I just mean like powers of x. So algebraic is like, x squared or the square root of 1 minus x cubed or things like that, where you don't really have any other kinds of functions showing up. Inverse trig, I think are both explanatory, what they are. And exponentials like e to the x or 2 to the x. So we use either integration by parts or substitution when we typically see a mixture of things. So for example, here's a mixture. The integral of x squared times e to the x cubed. It's got an algebraic term and a exponential term. So if I see a mixture like this, I'm first going to look for a potential U substitution. And here I see one. I can see that I'm going to let u equal x cubed. And then my du is going to be 3x squared dx. I like to isolate the x squared dx, so I'm going to say that 1/3 du equals x squared dx. And I'm going to rewrite my integral as 1/3 du e to the u. And then it's just e to the u, or I should say then it's just 1/3 e to the u. Of course, I've written this in the weirdest place, which is going to be 1/3 e to the x cubed plus c. So just want to stress, when you see a mixture of functions, usually the first thing you want to try to look for is there a good U substitution? And sometimes there will be, sometimes there won't be. So when there isn't a good U substitution, the next thing we look for is trying to do integration by parts. So for example, integral of x e to the 2x, or the integral of x squared cosine of 3x. These are both problems that would be doable using integration by parts. I'll just point out right here, I see an algebraic term times an exponential term. Here I see an algebraic term, or what I like to call any power of your variable, times a trigonometric term. Those are mixtures. I will point out, just because I know you both are aware, kind of the difference between U sub versus integration by parts is that when you're looking at a potential U sub, you'll usually see kind of like a function of a function, or the potential U choice stuck inside the other function. Whereas integration by parts really looks more like the straight multiplication, like you're multiplying this function times this other function. So if we look back at that previous example, you can kind of see this x cubed stuck inside the e to the whatever. Whereas here we just got x times e to the 2x. We've got x squared times, right? There's nothing kind of, there isn't really a composition of functions. There's so much. So integration by parts comes from the product rule. It's kind of neat, I think. So U substitution really is kind of like undoing the chain rule. And integration by parts isn't exactly undoing the product rule, but it certainly comes from the product rule. So here's where it comes from, or here's how it comes from the product rule. Comes from the product rule. So let's, and for some reason, I don't know who chose letters U and V when they did this however long ago, but someone chose U and V and we use them all the time. And of course, The two letters that are really easy to, if you're not careful, look similar to each other. So make sure you're careful when you write your u's and your v's, they look different. So if you take the derivative of u times v using the product rule, you get u times the derivative of v, which I'm going to write as dv, plus v times the derivative of u, I'm going to write as du. And now we're going to integrate both sides. So if I integrate both sides, well, the antiderivative of the derivative is just the function you started with. So the antiderivative uv prime is just, sorry, u times v prime is just u times v. And I'm going to integrate both of these things. I'm going to get the integral of u times dv plus the integral of v times du. And then we're going to solve for one of them. It doesn't actually really matter which one you solve for, but we typically isolate the u times dv one. So we're going to say that the integral of u times dv is equal to u times v minus the integral of v times du. This is the formula for integration by parts. I don't know if it's my coworker who came up with it or she learned it somewhere else, but she has always said this to herself as ultra violet super voodoo. And it's hard to forget. So when you do integration by parts, you're doing the ultraviolet super voodoo. UV, ultraviolet, super is the integral symbol, and voodoo is the VDU. Kind of silly, but it works. One sec. So the point here, what we're going to do is we're going to start with an integral that we're going to call the integral of u times dv. And we're going to make a choice for u and a choice for dv, so that when we rewrite the integral as u times v minus the integral of v du, the integral of v times du is supposed to be something that's easier to anti-differentiate than the integral of u times dv. So we're rewriting it. We're still going to get an integral, but it's going to be an easier integral.
I really like the mnemonic sequence because I never forgot
I tangent gets sexy. You can't forget I tangent gets sexy.
It's so useful.
Yeah, it is. I mean, it is. And then, you know, I got that from a student. They're like, oh yeah. So, you know, it makes me wonder, like, who was the first person? Probably never actually know, but it's kind of neat. So let's look at this problem here. This x e to the 2x. So typically, there's a couple ways we think about how we choose what is going to be what in your integral. Usually, you're going to choose u to be something in this order, which I was trying to write before, but I failed to. First, if you have it, you're going to choose u to be a logarithmic function. If you don't have a logarithmic function, you're going to choose u to be an inverse trig. If you don't have an inverse trig, you're going to choose u to be an algebraic term, or any power of x. If you don't have any power, you're going to choose u to be a trig, and then you almost never choose u to equal to e to the x thing. So in this particular example, I don't have a log, I don't have an inverse trig, but I do have an algebraic term. So I'm going to choose u to equal the x to the first, my algebraic term. Yeah, and I'll factor right now. Log, inverse trig, algebraic or algebra, or any power of x, trig, and then exponential. And there are some examples, I don't actually know them off the top of my head, but there are examples of things where you actually do choose u to be e to the x, but or something with e to the x in it, but they're few and far between. So when you're doing this process, you typically choose u to I usually choose u first, and then after you've chosen u, dv is everything else. You have no choices. Once you choose u, you have a choice there. U times dv has to be the entire integral. A couple things about u and dv. Your choice for u should get quote unquote simpler when you differentiate it. And it does, right? The derivative of x to a power becomes a lesser power, which is, you could say, simpler. And then on the flip side, dv should be something that is easy to anti-differentiate. It shouldn't get more complicated when you anti-differentiate it. E to the x is kind of the best example of that. When you anti-differentiate e to the x, it's still e to the x. Sine and cosine are also good examples because when you anti-differentiate sine or cosine, you essentially just get the other one back, and they're pretty much the same function. Here, our v, which is the antiderivative of e to the 2x, is going to be 1/2 e to the 2x. And now we're going to rewrite our integral, the integral of x times e to the 2x dx, the integral of our u times dv. We're just going to rewrite it as our u times v. So x times 1/2 e to the 2x minus the integral of v 1/2 e to the 2x times du. I'll mention here, we're not actually plugging in u's and v's. We're just using u and v to represent the things we've actually let them equal to. But we're actually plugging in what u is equal to and what d and v is equal to in terms of x, or whatever your variable happens to be. So now if we look at this, this remaining integral is something we know how to integrate. This is going to equal, well, see, I'm going to simplify this just a tiny bit and write this as 1/2 e to the, 1/2 times x times e to the 2x minus 1/2 times the integral of e to the 2x is another e to the 2x divided by 2. Let's see. And that is our answer. And if we took the derivative of this, not that I want to, we would get back the original function we started with, which should always be true of any antiderivative you find. If you take the derivative and simplify enough, you'll get back the function you started with. Question? Forever. There might be examples that could go on forever, but I mean, yeah, but the thing is, you don't. Well, it depends on it depends on what you have it with. So, well, for example, if we had something like, gosh, come on. It's something like the integral, say, x cubed times natural log of x dx. Again, I'm always going to first do a quick mental check just to see, is there a u sub that might make sense? There isn't. Letting u equal natural log of x, my du is 1/x. I don't see a 1/x in my integral, so that's probably not a great choice. So I'm going to try integration by parts. Right, I have a mixture. I have an algebra thing times a log thing. And according to my LI8 acronym, I should let u equal the log thing. So LI8 says u is going to equal the natural log of x. And then once I've chosen u, dv has automatically been decided for me. dv has to be everything else in my integral, including the dx. The dv is going to be x cubed times dx. And then the rest of it is just a process of finding the derivative of u. So du is going to be 1/x dx. And v, the antiderivative of x cubed, is going to be x to the 4th over 4. So now here's what happens. I don't think, you don't have to write the integral again. I like to write the integral again. So the integral of x cubed times natural log of x dx is going to be ultraviolet super voodoo uv natural log of x times x to the 4th over 4 minus the integral of v du, which is x to the 4th over 4 times 1/x dx. Now I have to stop here for a moment to mention, I've seen too many people do this integral wrong too many times to not say how I've seen it go wrong. For some reason, people really like to look at this and be like, oh, the integral is x to the 5th over 20 times the natural log of x. But we can't just integrate each part separately. Otherwise we wouldn't need the product rule, right? If you could just integrate each, things multiplied together by integrating each one of them and then multiplying the result together, we would have not needed to talk about this. But we do, because you can't just do that. The product rule is a thing. So fortunately, x to the 4th over 4 times 1/x simplifies really nicely. And we can just rewrite this as x to the 4th times natural log of x all over 4 minus 1/4 times the integral of x to the fourth divided by x is x cubed. And we for sure know how to integrate x cubed. It's going to be x to the fourth over 4. And there's our answer. Typically, no one should be asking you questions that go on kind of forever. Right? Or at least not without some sort of indication that you might see that kind of pattern.
So this should solve any mixture for most
I wouldn't say that. So what I would actually say is probably the majority of actual functions out there don't have a nice elementary function as their antiderivative. We are looking, I mean, there's a lot of functions that do, but in the infinitude of possible functions that are out there, most of them don't have a nice antiderivative that we can find. We have a large swath, or we have a swath of them that we look at because they can be antidifferentiated, but there's plenty of functions that don't have a nice antiderivative. Let's look at this next example. Integral of the natural log of x squared over x dx. So before I jump to doing integration by parts, I should look to see if there's a u sub, because this is a mixture, and there is a good u sub here. Right? If I let u equal the natural log of x, my du is just 1 over x dx. And this is exactly going to become the integral of just u squared times du. Which is just going to be u cubed over 3 plus c, which is just going to be the natural log of x quantity cubed over 3 plus c. Yeah, of course. No, it's all right.
I'm gonna be taking physics.
Sure.
7A.
Sure.
And I don't know how the co-class works, but I'm gonna be busy during the co-class,
Mhm.
so I wanted to.
For this co-class or the physical class?
For the physics class.
Okay.
And I don't know if Casey does YouTube videos or if I have to register for that.
Is Casey the one doing the class?
Yeah.
Oh, okay. I'm pretty sure Casey does do YouTube, but you could really ask him. Like not that you're not welcome to ask me. I just don't actually know if he I feel like he records this stuff and posts it.
It's on YouTube.
Yeah.
It's on
Yeah.
YouTube, yeah.
So, but I would also go talk to him. He's very friendly and he would certainly answer your questions and let you know how he's gonna run things. Yeah, I didn't realize, I thought Duff was the one doing that one. I sort of like, it's not, or maybe there's both. I actually don't know.
I think Duff is doing the 9
Oh, okay.
series, and then I'm taking the 7 series.
Okay.
Yeah.
So I made the assumption you're doing the 9 series just because that's usually what goes with the 21 series.
No, I'm actually in CBS, not,
Okay.
yeah, I'm not an engineer.
Interesting.
Next.
I can say 17 series, are you done?
Then.
Okay, cool. Right on. Cool beans. All right, so. Yeah, it's probably way easier to take 21A and 21B than take the 17 series, I gotta say.
It's so long.
It is, and it's it's wildly different. It's like 17C is so incredibly different than 21C. It's funny that they're both calculus classes. Let's look at, sorry, there was one problem in the beginning there that, yeah. So the word of warning is just to be on the lookout for U substitution, right? It's good to not always assume that our problem is integration by parts when we have a mixture. So here, again, kind of like the previous problem, I see a mixture of things. I have an algebraic thing times a trig thing, but before I start going down the road of integration by parts, I'm noticing, oh, it looks like there's a reasonable U substitution here. I can let U be the stuff that's inside the sine function, and then my du is just going to be 10x dx, or 1/10 du is just going to equal x dx. So right there's my 1/10 du, and this integral just becomes the integral of 1/10 times sine of u du. What's the antiderivative of sine? Negative cosine. Negative cosine, yeah. So we get negative 1/10 cosine of u plus c, which is negative 1/10 cosine of, a little scary, 5x squared plus c. Let's look back at that problem that we started with. what I wrote down in the beginning, which was, what was it? X squared cosine of 3x. Okay, so this one definitely does look like it's integration by parts. Like there isn't a good choice for u, whose du is also in there. So I'm thinking integration by parts, and I'm going to let u equal x squared. And then dv already chosen for me. It's cosine of 3x times dx. And du is 2x. My v is the antiderivative, which is 1/3 sine of 3x. So when I rewrite my integral, I get u times v. So x squared times 1/3 times sine of 3x minus the integral of v times du, which is 1/3 sine of 3x times 2x dx. What you'll notice is still a mixture. It's still an x times an x to a power times the sine of 3x, which means we're going to have to do integration by parts again. Now, some people kind of do something slightly different. It depends on what you want to do. One way you could do this is to let like dv be sine of 3x and u equal 2/3 x. I personally prefer to factor out the constant, even though that might actually not be the easier way to do it. I don't know. Now I'm kind of debating whether I'd rather do them. It's probably actually easier not to do that now that I think about it. Sometimes it's time, so you could factor out the 2/3, but I actually think in retrospect it's easier not to do that. So let's not do that. So let's say we're gonna let, and I guess I would probably rewrite this just so I can see it a little bit more nicely. I'm gonna say I have a integral of 2/3 x times a sine of 3x dx. And for my second integration by parts, I'm going to let u equal 2/3 x, and dv is going to be sine of 3x dx. du is 2/3 dx, and v is the antiderivative of sine of 3x, which is negative 1/3 cosine of 3x. So then we do it again. We get the whole thing. It gets to be kind of lengthy writing this all out. X squared times 1/3 sine of 3x minus u times v is going to be 2/3 x times negative 1/3 cosine of 3x minus the integral of v du, which is negative 1/3 cosine of 3x times 2/3 dx. And now we're almost done. We can totally integrate this constant times cosine of 3x. Question? You're right, I should. And that's probably why I actually do choose to pull out the 2/3, because it's easier to not miss that fact if you pull out a constant as well. Thank you. So yeah, so we should have minus all of uv minus the integral of v du. Yeah. So then we're going to get, let's write this as x squared times sine of 3x all over 3. And then this is a minus times a minus, so it's going to be plus 2/9 times x times cosine of 3x. Sorry, I summed them right one way, the other way. And then I've got minus a minus a minus. So minus the integral of 2/9 cosine of 3x, which is finally going to be, okay, 1/3 x squared sine of 3x plus 2/9 x cosine of 3x minus 2/27 sine of 3x, because I know I'm going to divide by 3 there. Whew. That was terrible. Yeah, question. Yeah, I would say this is a great example of why the tabular method is excellent. So let me stress a lot. There are only 3 types of integrals you can use the tabular method for. So tabular only works for the following types of integrals. The integral of a polynomial times e to a constant times x, or a polynomial times cosine of a constant times x, or a polynomial times sine of a constant times x. Here are the things that have to kind of be true for this tabular method to work. Your choice for u, which is going to be the polynomial, usually it's just x to a power, but that polynomial is the more general actual true thing. Whatever you're choosing for u, its derivative eventually has to be 0 if you keep taking repeated derivatives. And polynomials are really the only kinds of functions that if you keep taking their derivatives, eventually the derivative is 0.
Those polynomials, not square roots or.
Yes, you heard me correctly. Just polynomials, not square roots or any other stupid powers of x. Because again, like I said, the derivative, if you keep taking repeated derivatives, eventually has to get to 0.
It can't be negative.
Right, same reason. So I really do sincerely mean a polynomial, and all that means positive, I should say, non-negative integer powers of x.
P of x stands for polynomial.
Correct. So P of x is something like Cn x to the n plus Cn minus 1 x to the n minus 1 plus dot 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 plus all the way down to C1 x plus C naught. In reality, usually it's like, usually your polynomial is something like x to the n or x to the third or x squared, right? It's usually just x to a power. It's not usually more complicated than that.
Something like 1/2 x squared.
Yes. So polynomial, the only condition on polynomials is that the coefficients are real numbers and the powers are non-negative integer numbers.
So like x to the -1.
Correct. That would not work.
If instead of x, you have 1/2 x minus 1, so it comes with the value of 4. That's still a polynomial.
It's still a polynomial. Yep. So the reason, and then the reason we need the other part, the part that's going to be the dv part, to be either e to the a times x or cosine of ax or sine of ax, is because those are really the only three functions whose antiderivatives just kind of cycle. The antiderivative e to the ax is e to the ax divided by a. And then the antiderivative of that is e to the ax divided by another factor of a. And you just keep dividing by another factor of a. The same is true for sine and cosine. They're a little more complicated because they change signs. Like the antiderivative of cosine of 2x is sine of 2x divided by 2. And the antiderivative of that is negative cosine of 2x divided by 4, and so on and so on. But they don't really get more complicated in some way that you can't anti-differentiate them at some point.
That's why the other trig functions don't work.
Right, that's why the other trig functions don't work, because their antiderivatives eventually get too complicated if you keep doing them. So the way I usually write this is I'm trying to integrate something like we just did, like x squared times cosine of 3x dx. The way I usually do it is I like to make my u column and my dv column. So u is going to be my x squared. And then I'm going to take all the derivatives until I get to 0. So the derivative of x squared is 2x, the derivative of 2x is 2, the derivative of 2 is 0. And you do want to write the 0 because that's going to tell you how many rows of this thing you need for your dv. So then dv is the rest. It's cosine of 3x. I'm not going to write the dx because I don't want to. And we usually don't want to do it this way. And then I'm going to anti-differentiate on that column. So the antiderivative of cosine of 3x is sine of 3x divided by 3. The antiderivative of that is negative cosine of 3x divided by 9. And the antiderivative of that is negative, sine of 3x divided by 27. And then when we do is we take the upper leftmost u and we multiply it by the thing that's diagonally down to the right. And then we do that the same, we just keep doing that. And then it's plus x squared times sine of 3x over 3 minus 2x times negative cosine of 3x over 9 plus 2 times negative sine of 3x over 27. So it's just a plus minus plus minus plus minus plus minus until you get to the end. So this integral is equal to positive x squared times sine of 3x over 3 minus 2x times negative cosine of 3x over 9 plus 2 times negative sine of 3x over 27 plus c. Normally, if I was doing this, I would fix the signage along the way, but I wanted to write it like this just to point out it's really plus this times this, minus this times this, plus this times this. And then if I was fixing the signs, I would write this as 1/3 x squared times sine of 3x minus minus is plus 2/9 x cosine of 3x minus 2/27 sine of 3x plus c, which should be exactly the same as what we got before if I didn't make any mistakes. And it is. Question? It should be totally fine. Some people, I don't know. It's a totally valid method of integration. So you might want to ask your professor if it's okay if you use it. Usually if people want to use it, they'll kind of say, or they'll say you're allowed to use it. So what I would say is, if you're being asked to do like x squared times e to the x or x squared times sine, like that's reasonable to expect students not to use tabular. But really, after x squared, after that, it's just so much work to keep doing the repeated integration parts. So, yeah.
And then, what you mean by positive, negative, positive? That's the sign that comes after that term, right?
No. So it was literally. So let me do this here. It was plus x squared times sine of 3x over 3.
Oh, okay.
And it was minus 2x times negative cosine of 3x over 9. And it was plus like that. Yeah. So that's how that works. And then you can kind of apply it to lots of examples. Well, not lots, to a very select few examples. But they do come up relatively frequently. So for example, if someone said, what's the integral of x cubed e to the negative x dx? Instead of doing integration by parts 3 times, I'm going to make my u column, that's x cubed. And I know what I want to round this up. Sorry, one more thing here. I just want to write, on the u side, we are differentiating as we usually do with the u thing. And on the v side, or on the dv side, we are anti-differentiating. Which I think is relatively clear here, but sometimes with the e to the x ones, especially, it can be not 100% clear that you're actually doing the antiderivative instead of the derivative, but you are. So for this one here, I would let u equal x cubed, and then all my derivatives are going to be 3x squared, 6x, 6, and 0. And my dv is going to be e to the negative x. And the antiderivative of that is e to the negative x divided by -1, but that's the same as multiplying by -1. It's going to be negative e to the negative x, and then positive e to the negative x, and then negative e to the negative x, and then positive e to the negative x. And then same deal. So without doing all those steps, our integral here is going to be negative x cubed e to the negative x minus 3x squared e to the negative x minus 6x e to the negative x minus 6 e to the negative x plus c. One times. Okay, yeah, we're got that. Oh yeah, we have that, and that, and that. I want to do that next, though. Yeah, let's do one of those. So I feel like this is a good time to kind of, yeah, we should do that one next. So let's say, yeah, we'll come back to those other examples, but I want to do this next one. So we need a whole page for this next one. So there's another style of integral that kind of comes up frequently, and it's very much its own thing. So this is kind of integration by parts with a twist. We'll do the integral of e to the 3x times cosine of 2x dx. I will say the way we solve this problem is similar to another problem that I like a lot, which is the integral of secant cubed, which we'll probably talk about at some point once we get to the trig integral stuff. So here technically you could actually make either choice for u and for dv. Now I'm going to follow my Lie8 acronym, and I don't have a log, I don't have an inverse trig, I don't have an algebra term, so I'm going to let u equal the trigonometric thing. So here we're going to let u equal cosine of 2x, and then my dv is going to be the rest, which is e to the 3x dx. I will point out though that you can make the opposite choice. You can let u equal e to the 3x here and dv be cosine of 2x dx. It's fine to do it either way as long as you are consistent in what you do, meaning when we do the second integration by parts, we have to make the same type of choice. You let u equal the trig thing here, you have to let u equal the trig thing in the next one. You let u equal the e to the x thing here, you have to let u equal the e to the x thing. Let's write down the rest of this. My du is negative sine of 2x times 2 dx. My v is 1/3 e to the 3x. So now we're going to write this as uv, so 1/3 e to the 3x times cosine of 2x minus the integral of v du, 1/3 e to the 3x times. So instead of writing negative sine of 2x times 2 over here, I would probably pull the negative out in front and write it as plus sine of 2x times 2 dx. Yeah.
Function, for an integral is gonna lead you to doing multiple integration of parts. Like, how do you know when to use that?
So usually, I mean, so typically there's not, it's usually like x to a higher power times sine or cosine for e to the x.
Oh,
So usually we mostly see repeated integration by parts in ones that could be done tabulated. There are some exceptions to that. Like for example, the natural log of x quantity squared definitely does require repeated integration by parts and it's not tabular. But there are there are not a lot of ones other than the tabular ones that really do require any repeated integration by parts. This is an exception as well, but it's not tabular. So yeah. So I would probably choose. I kind of want to do the other thing I was trying to do before. Here I don't have that minus sign problem, so I could let for this next integration by parts. No, I'm going to do it. Who am I kidding? 1/3 e to the 3x cosine of 2x, and then let's factor out the 2/3. Have an integral of e to the 3x times sine of 2x dx. Now we're going to do integration by parts again. We're going to let u equal sine of 2x and dv equal e to the 3x one more time dx. And du is cosine of 2x times 2 dx, and v is e to the 3x divided by 3. So if we write this down, we've got 1/3 e to the 3x times cosine of 2x plus 2/3 times my ultraviolet super voodoo, which is going to be u times v. So e to the 3x over 3 times sine of 2x minus the integral of v du, which is e to the 3x over 3 times 2 cosine of 2x dx. Now I'm going to multiply this out and I'm going to make it really kind of extra, maybe explicit about what's going to happen here. This is all of this is what this integral is equal to. So this integral of e to the 3x cosine of 2x dx is equal to 1/3 e to the 3x times cosine of 2x. I'm going to distribute the 2/3 and say 2/3 times 1/3 is 2/9 e to the 3x times sine of 2x. And then I'm going to multiply the 2/3 here and factor out the other 2/3 to get a minus 4/9 integral of e to the 3x cosine of 2x. And you might notice that in the integral of e to the 3x cosine of 2x, I have it equal to something with e to the integral of e to the 3x times cosine of 2x. So what we do, here's the twist. We're going to add this to both sides. So a whole integral plus 4/9 of an integral is how much of an integral? Not 2 times. It would be 2 times if we didn't have these weird coefficients, like if this was just an e to the x and a cosine of x, you would get double it. But here, since I have a 1 of a thing plus 4/9 of a thing, I'm just adding the coefficients. And 1 plus 4/9 is going to give us 13/9. So we're going to have that 13/9 times the integral of e to the 3x cosine of 2x dx is equal to 1/3 e to the 3x cosine of 2x plus 2/9 e to the 3x times sine of 2x. And then finally, multiplying both sides by 9/13, we get that the integral of e to the 3x cosine of 2x dx is equal to 9/13 times, I can fit this in, I promise, 1/3 e to the 3x cosine of 2x plus 2/9 e to, I should have factored out e to the 3x, e to the 3x sine of 2x plus c. And that is always what happens when you integrate e to, so this is generally true, or generally the way we do it for anything that looks like e to the a times x times cosine of b times x, or the integral of e to the a times x times sine of b times x. This is the general way that this always works. So if you see the integral of e to the x times sine of 5x, you'll know that you have to do this integration by parts twice. And then the thing you're trying to find comes back up again, and you add it back over to the other side, and then you divide by the coefficient, and then there's your answer. It kind of feels like you didn't actually integrate it, right? To me, it feels that way, or at least used to. Seems what? It is. But this is a totally valid answer that does not have the integral in it at the end. If you take the derivative of this, it'll for sure equal that. Kind of cool. All right, let's go back to where we were before. So there's some other weird functions that we integrate using integration by parts, like the integral of inverse tangent. You're welcome. You too. See you on Wednesday. This is an example of a function that might not look like it's an integration by parts problem because it doesn't really look like a mixture, but it is, because, so here's what I'll say. Technically, the dx part can count for like your algebraic term or for your power of x. It's like x to the 0. Kind of dumb, but it works. So here, we're going to use integration by parts, and we're going to let u equal the only thing that we can choose u equal to, which is the arctangent. And then my dv is everything that's left, which is just dx. And then our du is the derivative of arctangent of x, which is 1 over 1 plus x squared dx. And our v is equal to the antiderivative of 1, which is x. I'll point out, because I think it's, so we're probably going to talk about trig substitution in the near future. And it's nice to kind of know that when you see 1 plus x squared, that goes with tangent. I'm not going to explain that fully right now because there's more to it than that. But really, I will say this more again later. The derivatives of the inverse trig functions kind of hold the key to knowing what trig substitution to do later. So we'll leave that there. I'll say it again later, but I just want to point out it's kind of nice to know. So it's good. So you definitely do want to know the derivative of arctangent and arcsine and arcsecant. All right. So, but now we're just going to do the integration by parts formula. So the integral of arctangent of x is going to equal u times v, so x times arctangent of x, minus the integral of v times du. And then if we look at our integral of v times du, which is the integral of x over 1 plus x squared, we do a u substitution. So I would probably off to the side say, oh, the integral of x over 1 plus x squared I'm gonna let u equal the 1 plus x squared. And my du is gonna equal 2x dx. So my du over 2 is gonna equal x dx. So I can rewrite this integral as the integral of 1/2 du over u. And the integral of that's going to be 1/2 natural log of the absolute value of u, which is 1/2 natural log of the absolute value of 1 plus x squared. And just like I usually point out, I will point out here that we could drop the absolute values, and you'll see most solutions manuals drop the absolute values because 1 plus x squared is always positive. So typically we end up writing this as x arctangent of x minus 1/2 natural log of 1 plus x squared plus c. And that is the antiderivative or integral of arctangent of x. I would encourage you to, on your own later, try the integral of the arc sine of x. Or arctangent of x. I will mention it is very, very similar. You do the same sort of process, and then you end up getting an integral that also requires a u substitution. And in case you've forgotten, I'll remind you. In fact, I'll remind you over here. So I think it's worth knowing. The derivative of the arc sine of x is 1 over the square root of 1 minus x squared. And the derivative of arctangent, even though I know I've already written down on this page, I'll write it again, is 1 over 1 plus x squared. And finally, the derivative of the arc secant is 1 over possibly the absolute value of x times the square root of x squared minus 1. Though some people teach it where you don't have an absolute value there, so it can go either way. So back to that comment I was making before, later on in like a week or two, we're going to see that when we do trig substitution, if your integral has a 1 minus x squared, that means the trig sub is going to be sine. And if your integral has a 1 plus x squared, that means the trig sub is going to be tangent. And if your integral has the x squared minus 1, it means the trig sub is going to be secant. Which is kind of cool. And there's more to it than that, but like, we don't need to talk about this yet. It's really because of how the trig identities work. Right? If you plug in sine for x, you get 1 minus sine squared, which is cosine squared. And if you plug in tangent for x, 1 plus tangent squared is secant squared. And if you plug in secant for x, secant squared minus 1 is tangent squared. So that's the reason why those are the choices for your trig subs. And again, we haven't actually talked about trig substitution yet, but we're almost done. You can probably stop. It's 150, since it's 158.
Problem again with the integral of e to the 3x times cosine of
Yes, totally.
Thank you.
You're very welcome. We didn't do natural log. We'll have to do that one on Wednesday.
Yeah, and I was also curious, because you said 2 or more functions inside an integral, but what about if there's 3 or 4?
Typically, so usually 3 or 4. So really, I said or more to kind of cover my bases. It's usually just 2 types of functions. You don't usually see a mixture of 3 types of things unless, yeah, I mean you could, but then like, so I'm trying to think of something now, like what if you saw something like, oh, that's gonna be stupid, James. Or maybe you had something like the integral of 3 or more. Maybe you have, I don't know, this is gonna be stupid. I'm trying to make something up that's not gonna suck, and I feel like e to the sine of x times cosine of x times sine of x. And one, like, that's only 2 types of functions, really. Let me get something else in there. I don't know. This one would be a u sub and then inverse of my parts, the way I've written this one here. But yeah. Yeah, usually it's really not 3. It's usually just 2 types of functions.
And then also, now that you mention it, can you do integration by parts once you've done a u sub?
Yes, you can.
So like you could do it with du and u.
Right, so here's what I would say, in fact, here's an example of that question you just asked. So let's say we were integrating this function. Sine of x times cosine of x times e to the sine of x dx. If I was going to integrate that, well, that looks terrible. I see there's a u substitution there. So now here's what I'm going to do because I know what's going to happen. I'm going to do a u sub, but I don't want to pick the letter u because I like using u and v in my integration by parts. I don't like you don't want to let u equal u if you've already used u. So I'm going to use any other letter. I'm going to pick t. I'm going to do a u substitution where t is equal to my sine of x. And then my dt is equal to what? Yep, cosine x dx. So here's my dt. And then I'm left with what? Well, I've got dt, and then I still have a sine x times e to the sine x, which is going to turn into t times e to the t. And now I'm going to do integration by parts because I have an algebraic thing times an exponential thing. And I didn't use it my u. I mean, you can totally use it. People then kind of use w instead. But I'm so used to writing the formula as uv minus the integral of v to u that it's hard for me to think of it as like wv times the integral of v to w. So I kind of use my knowledge of what's going to happen. So then I would let u equal t for my integration by parts. And my dv is e to the t dt, and then my du is dt, and my v is e to the t. So then this becomes u times v minus the integral of v du, which then is going to be t e to the t minus e to the t plus c. But then I have to plug back in my u sub. Like, oh, but t was really sine of x. So this is really sine of x times e to the sine of x minus e to the sine of x plus c. But yes, you can totally have a u sub and an integration by parts.